target in sight. Where in hell is Major Kong?
Hey, what about Major Kong?
Quickly. Well, the first one we don't have to explain, we're already there. The second one, Comoving frame, is very natural. Comoving frame says, this is very natural, it's invented, once every month by somebody since mid-19th century at least. So it has lots of names. I'm using the most suggestive name. In the book, there are other names listed. And Comoving frame says the following thing. At every place in my state space, at every state, there is a bunch of vector fields associated with it. Dynamics tells me I can go this way. So this velocity vector is my equations of motion. It's a field as defined every place over state space, and that's what I integrate to get trajectories. However, because I have a symmetry, there are more vectors, and they tell me that I can move, for example, in SO2, I can move in this direction. I can move tangentially to the group orbit without changing the physics. So there is a tangent vector for every parameter that I can think of. So let me draw this for more general symmetry than just SO2. So the idea is this. There is my state space, and in the state space there is a group orbit. So there is something I'll call M. This little label saying that if there is a point in the place I have following objects. I have my full state space velocity. Then I can always define the normal. So here is the normal vector. So this is normal to the group orbit. It's a surface whose dimension is the number of free parameters. I'm here assuming there are two parameters that have to do with group orbit. The whole thing is embedded in a big space. So it's embedded in my full state space coordinates x1, x2, x3, x zillion. In textbook examples, zillion is 3, 4, 5. In applications, it can be really a million or a few 100,000. So there's a point in the state space that's a state of the system, so that's like a snapshot of turbulence. We have tangents. One parameter, we label it 1, so tangent in this direction, tangent in that direction. And if there is capital N parameters, it's a hypersurface that we have put a plane on, so it's a tangent space. And you'll be happy to hear that this is now a tangent bundle because every point in space owns n+1 tangents. One is time, and then n continuous symmetry. Locally, I'm allowed to go in different ways. Well, then there is an obvious way to go in. And this is to say, you know what I would like to do? I mean, moving along the group directions is boring because physics doesn't change along directions. So that's inefficient. And indeed, when you do simulations of systems with continuous symmetries, you'll find lots of motion having to do with moving almost in the symmetry plane. And what it means experimentally, for example, what happens in a pipe, is you go around, run together with this thing, the symmetry direction is down the pipe, and the dynamics will be such, because you're moving in the pipe, that it has a very large component in symmetry direction and very little component transverse to it. But you only care about the transverse component. Let me pick the new field in such a way that I'm orthogonal to this. So that's called moving frame, and what it means is, I can try to draw another picture of what the thing looks like. If you start at some group orbit, so you are at point x at time 0, and the group orbit, it's the group orbit which is all the things you can get by continuous transformation, usually a bagel, but I'm just looking at a local neighborhood, mx at 0, then time t later, you'll end up on mx at t, so you'll end up someplace x at t. And that'll be your lob trajectory. Your equations of motions would give you this trajectory. But all along the way, I'm always allowed to choose anything on these manifolds to represent it. So what I do instead is I start out in direction here that's orthogonal at this instant. So I picked my condition on this decomposition in such a way that the new v prime, but I choose the new one to be normal to the surface. So I just choose that, because I can do this at every point. I know what all the guys are, so I can actually choose to just move in such a way I don't move in the group directions. What has happened here, I have introduced norm, because I'm introducing condition that says the new velocity at the point x is chosen by demanding that it's normal on all the tangents. This is a moving frame condition. At any instant, I'm always moving normal to my group. So what happens is I get another trajectory. And that trajectory, f hat at time t, starting at the same point, is someplace else in the state space, but at all instants in time, it's related by group symmetry to my original. So I haven't lost any physics. I've just gone to a natural frame. You just take this equation and you dot it. And you find that demanding that this thing on the left side is 0 gives you an equation for phi dot. So you find out that you now have v prime equals the old v plus phi dot in a group direction, and dot means sum over. As I cheated in my derivation, I'm not sure about it. It's true for abelian groups at least. Sum over all the group directions, continuous symmetry direction. That's what this dot means. But now I have a condition that enables me to compute phi dot. And that condition, when you work it out, says that that's the same thing as dotting v here. And I have it for every parameter. So dotting v into the tangent in direction of that parameter. We get a simple formula that says point x dotted in t at a point x. That came from dotting this guy. We dotted this. We got 0 on the left-hand side. I might have a minus sign, I'll let you. Now I have an actual calculation. I've changed the coordinates and I've told you how I've changed them. I've changed them by requiring that at every instant in time I don't move in group direction, because that seems stupid. I am free to do it. And when you think about it, when we fancy it up, this is what you do, for example, in general relativity. When you go to the proper frame, it's a frame where you see least effect of, your general symmetries. You see it in a locally Minkowski frame, so you're doing things where the space is least curved. So it's a natural choice. You can see now what's happened is that so the velocity lives in a space, in a whole phase space. But we have now also a reconstruction equation. We know this theta because we can integrate this equation. So we know that if we move on this frame, we know how to get into that frame because we can integrate theta dot. So we made a change of coordinates into something that's locally group theory flat, and we only see the dynamics, which is transverse to the group theory, and we can compute this as the integral 0 time d tau phi dot tau. So that's called reconstruction equation. We haven't lost any information, but this choice seems very natural. It's tested on the simplest case. An example is a relative equilibrium. And if you remember what relative equilibrium was, if you had your state space and in it there was a group orbit. Just SO2 group orbit. So this is SO2 group orbit. And as I looked at the point on that group orbit, and you're not drawing group orbit as they really look like. They're complicated for nonlinear problems. They're not circles. As you looked at the tangent space and you looked at the velocity for this relative equilibrium, it turns out velocity is tangent to the group orbit. So you have a relation that says velocity is, at this point, something that points the same way as the group orbit. So velocity is d-dimensional vector, group orbit is d-dimensional vector, they're all embedded in the whole space. And there is a proportionality thing that's called phase velocity. And dimensions that this is length over time. T is proportional from its definition, which I might have erased here, right here, is proportional to the length, how far away from the origin. So this, you think of this as the angular velocity. So this is 1 over time kind of thing. You see lots in mechanics. So now, if this happens for relative orbit, then you stick this information in here, and you will find time is 0. What does that mean? You've gone in co-moving frame, you have no motion along the group orbit. So the thing that used to just whip by when you're looking at a pipe, now you're running with the pipe and you see a stationary object, a traveling wave. So that's the simplest example of use of co-moving frame. And this is the definition, so this is the trivial case. All the applied mathematicians always do this. They like to look at relative equilibria or traveling waves. And they all understand you should go into co-moving frame. Now you might ask yourself, when I develop this theory of chaotic motions, I also care about periodic orbits, which are now called relative periodic orbits. So is that a good definition? It seems like a very smart thing. There's a rocket, I sit on a rocket, the rocket does something and it just comes back after one period. Well, it turns out, in my opinion at least, this is not good for relative periodic motions. Why is that? So easiest thing is to actually just try it. So we'll give you problem sets in which you try it. But basically it's for the same reason why Foucault pendulum is not just a simple pendulum. Foucault pendulum has the idea that you're sitting on a rotating earth, and the pendulum in its own frame looks periodic to itself. Every period it comes back. But when you actually sit in Paris and you look at it, the thing precesses and it moves. It tells you that you're on a curved space. It tells you that there's some interesting velocity due to having gone to the Comoving frame. So I won't work it out, but that's kind of standard mechanics. The problem with this, from our point of view, is that it doesn't reveal the hidden periodicity of motion that's embedded in state space, because of all the things that move on a torus. So last time I told you that the important thing, the moment you had a continuous symmetry, dimension of your periodic motion increased. And the relative periodic motion, what it did is that if you started someplace, so you start someplace here, so this is your trajectory evolving in time. It goes and does all kinds of stuff, and when it finally comes back, it came back shifted in the group parameters. So, you looked something, it vanished, it did complicated things, it was swimming, changing shape. At an instant, it looks the same, it just displaced someplace. So physically it's the same. So that was the relative periodic orbit. Relative periodic orbit said that x at a period is what happens in a full state space at a time, having started at 0 point, but shifted by a parameter that has to do with this periodic orbit. So there's a transformation here. So the object that's invariant is the torus, not any particular trajectory. So now when you investigate comoving trajectories, they have a property that every place they go normal, but they have a property they're always normal to the orbits. So when they come back, they're normal. So this is same orbit in comoving frame. Goes around, and what it does is it comes back also normal, but still displaced. And this displacement, might be very profound. I just don't know. I think it's called geometric phase. I think it's called geometric phase because it's one unique trajectory of all possible trajectories, because we have this immense freedom to choosing trajectory, but comoving is the only one that's comoving. It's the only one that's perpendicular. So this is geometrically well defined. No other thing that investigates the torus is particularly well defined. It depends on my convention. But this one is intrinsic. It just says, I have geometry and I always move normal to the tangent bundle, the group tangent bundle, that's it. In other subjects, like in quantum mechanics and classical mechanics, it has a very good pedigree. It was studied roughly since the 1805 or 1806. The first example of this is by a fluid dynamicist or oceanographer called Jeffries, or physicist. And in the 60s and 70s, it became famous as Barry's phase in quantum mechanics. So it's an important thing that people can measure. And now, if you could tell me how to measure this in fluid mechanics, you would be famous, and it would immediately write it up. So this means something. It means something because it's obviously preferred of all possible things. So for example, when a swimmer goes to Havana and swims, she lives in this frame. That's her frame. That's the natural thing. So if you tell me that I look at turbulent flow, I shine the light this way and that way, and I measure some number, which is intrinsic to geometry, to the symmetries, it'll be wonderful. I just can't think of a physical effect that it has. So keep in this mind, comoving frame, the way we define it, it's computers talking to computers, because this transformation depends on measuring tangents. Yeah. So I know how to do it computationally, but I don't know how to do it in a lab, experimental. I don't know what experiment to do to measure this frame. But maybe it's very profound, very good. I will leave it at that, because I don't know what to do with it. I will instead, guys, I mean, you haven't said a word yet. I'm grateful, but still, it's a little worrisome. You know, some of you should really worry about this stuff. So here is the comoving frame equation. And now I will explain what I think personally is the way to analyze turbulent or chaotic phenomena. And the distinction is the distinction between, you know, just being self-centered and thinking what's happening to you. That's comoving frame. You go around and, yeah, you don't care what other possible paths through life are. But when we're trying to describe complicated, chaotic, and turbulent motions, the whole point is that we describe all possible motions of the state space and then we make predictions, because every particular trajectory itself in chaotic dynamics is not predictable beyond some finite time. But as we will see in the remainder of this course, the behavior of totality of them, likelihood that something will happen, you know, that's carried by deterministic flow. So it's not probabilistic, it's not probability theory, it's theory based on exact determinism. But that theory requires averaging over all possible motions. And we don't, at least I don't get any wiser at the comoving version. And it'll turn out the other version is very close to this. So the only difference will be here. So this is comoving.